Electricity is the physical movement of electrons through space, but to get those electrons to move, you need a push. We call that electromotive force, or voltage. It is the pressure driving the particles forward. When that pressure is applied, the actual physical flow of those electrons, much like water moving through a pipe, is the current. And whatever physical material those electrons have to move through creates friction. This property, which opposes the flow, is resistance. On their own, these forces act independently. If you apply high voltage to a space with almost no resistance, the resulting energy is chaotic, unpredictable, and often dangerous. To control this energy, we have to find the specific rule that forces these variables into a permanent, predictable equilibrium. In a closed system, these three elements are locked together. The voltage applied to a circuit is directly proportional to the current flowing through it. Mathematically, we define this relationship as V equals I times R. This creates a concrete physical benchmark. It takes exactly 1 volt of potential to push 1 amp of current through 1 ohm of resistance. This chart shows the relationship between voltage on the vertical axis and current on the horizontal. For a simple resistor, notice that the relationship is a perfectly straight line. Any point on this line represents a balanced system. If you fix the resistance of a wire and increase the voltage, the universe dictates that the current must increase at that exact same rate to maintain the ratio. This predictability is the foundation of electrical engineering. It lets us calculate exactly how a circuit behaves before turning on the power. We can see this balance in action by changing the environment. Imagine a circuit where the internal pathway narrows, physically increasing the resistance. If the voltage remains the same, the immediate effect of that added friction is a drop in the current. The electrons physically cannot move through the bottleneck as quickly. But if the system requires that original flow rate to function, what has to change? To maintain the ratio, you have to push harder. The voltage must increase to force that current through the high resistance path. This struggle has a physical consequence. The energy used to overcome high resistance is dissipated as real power, which we experience as heat. Every circuit behaves like an ecosystem, constantly trading force and flow to ensure the equation never breaks. Simple circuits use a steady flow, but alternating current, or AC, constantly shifts its direction back and forth. This shifting environment requires new components to manage the energy. An inductor coil creates a magnetic field that physically resists any change in the current's flow, acting like electrical momentum that fights against the alternation. Then there are capacitors, which react to the changing voltage itself. As shown here, a capacitor stores charge across an insulating gap. By holding and releasing that charge, it creates a pushback against the applied pressure, resisting the cycle of the alternating voltage. In an AC circuit, the friction of resistance combines with this reactive opposition from the inductors and capacitors. This total effect is called impedance, or Z. Even in this complex alternating world, the balance holds. The law simply evolves to its final form, V equals I times Z. This law governs the macro scale. It dictates the massive voltage required to push current over hundreds of miles of transmission lines to reach our cities. Yet the exact same equilibrium governs the microscale, controlling the delicate flow of electrons within the microscopic pathways of a processor. Across every scale, the rule is the same. Nothing moves without a push, and every path presents friction. George Ohm was the first to prove this universal balance in 1827. Today, his name is synonymous with the property he discovered. Because Ohm's law provides a predictable mathematical equilibrium, we have the means to safely control the invisible forces that power our world.